So let us start with something that should be simple. Let's say the drag assistant from the last couple of videos, the support bot answering questions of a big pile of company docs, actually did well. And it's a real product now. Lots of users. So we did the obvious thing and put it on more than one GPU, the chips that run the model. Let's say six of them, all running the same model. A request comes in and we have one small question to answer. Which of these six GPUs should handle it? And honestly, we already know this one, load balancing. Send it to the least busy one and the one with the most room. Safe, boring, correct. So we do exactly that. We find the emptiest GPU, barely any load, and send the request there. And it did comes back slower. And that's the whole puzzle of this video. The least loaded GPU was the wrong GPU because the busier one already had half of this request work sitting in its memory, ready to reuse. And the empty one had to redo all of that reading from scratch. So, which server is free? The question that ran our entire load balancing video quietly stopped being the right question. So, in this one, we build a thing that actually answers it. The layer that sits in front of a fleet of GPUs and decides for every request where it goes, whether we even accept it, and when to buy more machines. And it turns out that layer looks like a load balancer that had to grow up. Okay, so let us zoom out. At high level, the last video was inside one GPU worker, watching a single prompt go through the machine. And just a quick reminder, because this whole video leans on it. When a prompt arrives, the model first reads the whole thing, that is prefill, the wait before the first word. Then it writes the answer one token at a time, that is decode, which is why answers stream. And the model's working memory of the conversation kept in the GPU memory, so it does not reread everything on every token. That is the KV cache. And it is big and expensive. That was the last video. One engine. This video is what happens when you have many engines. And the moment you have more than one GPU, honestly, inference stops being an AI problem and turns back into a plain distributed systems problem. Who routes where? Who is overloaded? Who just died? The same questions as any fleet of servers. Except the unit of work here is really strange. And that strange unit is exactly what breaks the classic answer. So let us lay the fleet out once. At the front, a gateway, the front door. It takes the request in, behind it, the piece that matters most, the router, whose whole job is to look at the request and pick which GPU worker handles it. Then a little admission gate, and the gate is allowed to say, no, not right now. Behind it, the pool of GPU workers, each running the model, each holding its own KV cache. And off to the side, a planner watching the whole fleet, deciding when to add or remove GPUs. Now, here is the one idea that ties this entire machine together. So, hold on to it. Every decision these pieces make is really answering the same question. Not which GPU is free right now, but which choice buys us the cheapest future. Cheapest in first token time, in wasted compute, in money. The router is honestly less a calculator and more like an air traffic controller. It cannot make every plane land first, so its real job is deciding who waits and for how long. And at high level, the machine answers that in three loops, and the whole rest of this video is just these three. There is a fast loop that runs on every single request. The router, there is a slow loop that changes how many GPUs we even have, the planner. And there is a protection loop for when there is too much traffic or something breaks, fast, slow, protection. Keep those three things in your head, and everything we build drops into one of them. So let us start with the fast loop. The router looking at one request because it turns out even describing the request is where the classic model falls apart. So the router is staring at our GPU workers, trying to pick who gets the next request. And the classic load balancer has one favorite number for this: how many requests or connections each worker is currently handling. Fewer is better, send it to the one with fewer. So let us look at our workers through that lens. Worker A, 2 requests, worker B, 2 requests, worker C, 2 requests. Perfectly balanced. The load balancer is happy. Pick any of them. But now let us actually look at what those two requests really are. On worker A, there are two short chat messages, maybe 200 tokens of memory between them. On worker B, there are two long rack questions, each one dragging around 40,000 tokens of KV cache. So that worker is nearly full, its memory almost gone. And on worker C, the two requests happen to share the exact same system prompt and documents as the new request arriving. So worker C has already done most of this new request reading. So two requests told us basically nothing. Three workers identical by request count and completely different in the only two things that actually matter: how much memory is left and whether the expensive reading is already done. And this is the shift. For a normal web server, one request is roughly one unit of work. They are all about the same size. For an LLM, one request can be one line thanks or it can be an entire book chapter. Same count, thousand times different cost. So a good router does not count requests. It prices them. Before it routes anything, it turns the request into little cost cart. How much prompt tokens, roughly how much output we expect, which customer it belongs to, its latency target, and a fingerprint of its prefix so we can check who already has it cached. And here is the catch: the one field it would most love to have, the exact output length, is the one thing it cannot know it. It has to price the request before it knows how long the answer will be. So it's pricing under uncertainty. And hold on to that. It's the reason this whole problem stays hard. So now the router can see the real state, and one of those fields matter more than the rest: the prefix fingerprint. Remember prefix caching from the last time? If a new request starts with exact same tokens as the one we already handled, the same system prompt, the same document, we can skip rereading that part completely. We already built its KV cache once, we just reuse it. That turns a slow, expensive prefill into almost nothing, which saves the first token weight and saves real money as well. So the router has an obvious idea. Just route every request to the worker with best cache match. Maximize the reuse. And honestly, would you do anything different? It looks obvious, right? So let us do it and watch what happens for a while. It works beautifully. Requests that share a popular system prompt all land on the same worker. All hit the cache. First tokens come back fast. Nice. But think about what we just did. Every request that shares that popular prefix goes to one worker. So that worker gets more and more traffic while the others sit idle. Its queue grows, its memory fills. And now requests are landing on a worker that has a beautiful cache hit and no room to actually run them. So they wait. The cache hit was perfect, and the first token time went red anyway because we piled everything onto one worker while the rest of the fleet sat idle. So cache affinity on its own builds a hotspot. Okay, so now we overcorrect. Forget the cache, just balance the load. Spread every request evenly, the classic way. Now, nobody is overloaded. Everything is even. But we just threw the cache away. Requests land on workers that have never seen their prefix. So every single one rereads the whole prompt from scratch. The reuse collapses, and now we are paying in compute and in first token time to redo work we have already done and just threw out. So here is the tension, and it is really the heart of the whole video. The best cache decision and the best load decision are usually not the same worker. Route by cache only, you overload one worker. Route by load only, you burn money redoing work. And if this feels familiar, it's the old sticky session problem from load balancing. Send the returning user back to the server that remembers them, except now the thing being remembered is GBs of expensive GPU memory. So sticky got very costly to get wrong. So, what do good routers actually do? They don't pick a side, they score. And this is the important part: the router scoreboard, and it's the only thing to hold in your head for the rest of the video. For each candidate worker, it adds it up. How much useful cache does this worker already have? That's a credit. That's good. Minus how much loaded it already is. Minus how full its memory is. Minus how much this would hurt its latency target. Every worker gets a score, and the router takes the best total. And most of the time, that winner is not the pure cache worker and not the pure loaded worker. It's the one in the pure middle, with enough cash to be worth it and enough room to actually run it. And this isn't just theory. The SG-Lang router does exactly this: cache-aware scoring, and they reported roughly double the throughput over plain load balancing just by not being blind to cache. And it's not only them. VLLM's production stack and NVIDIA's Dynamo landed on the same cache-aware routing. So the scoreboard is real, and the whole industry is quietly converging onto it. So that's the fast loop. Price the request, score the workers, route it. But routing quietly assumes the fleet can cope. So now the protection loop. What the fleet does when it cannot. And the first case is the simplest: too much traffic. The router is scoring beautifully, but the requests just keep coming. more than the whole fleet can handle, no matter how cleverly we route. Every worker's queue is growing. Now what? And the tempting answer is accept everything. Do our best, be a good service, but watch what that actually does. If we keep admitting requests onto workers that are already full, everybody's request slows down. The queues get so long that even the tiny fast chat messages are stuck behind a wall of heavy work. So, by trying to serve everyone, we make everyone miss their latency target at the same time. We didn't help anyone, we just spread the pain evenly across all of them. That is exactly how an overloaded system falls over. So, a mature serving system does something that feels wrong the first time you see it. Under real overload, it says no. This is admission control or load shedding. The gate watches a couple of honest signals. Is KV memory over? Let's say 90%. Is the queue longer than we can possibly clear in time? And once it crosses the line, new requests get turned away cleanly with a try again in a moment, and it sheds the right ones first. The low priority batch job gets deferred before the paying interactive user. Now, rejecting isn't the only tool. Some systems queue you, some degrade quality, some fall back to a small cheaper model. But the point underneath all of them is the same. A system that never says no isn't kind. It's just a system that keeps saying yes until everything is broken. Saying no to one request is how you keep your promise to the thousand you already accepted. This shows up in the real systems too. Mooncake rejects early under overload. Dynamo returns a 503 with retry guidance. The fleet is allowed to protect itself. That was the fleet protecting itself against overload. But there is a quieter unfairness that shows up even when we are not overloaded. The moment many customers share the same fleet, and the usual way to be fair is a rate limit everyone gets. Let's say 100 requests a minute, equal counts, equal footing, right? But watch what that lets happen. Customer A sends 100 short charts, 50 tokens each. Customer B sends 100 giant rag jobs, 50,000 tokens each. Same request count, both politely inside the limit, but customer B is doing about 1000 times more token work, and because these requests share the GPUs and the same KV memory, B's giant jobs don't just use more, they crowd A's little requests right out of the batch. So customer A isn't just slower, A ends up waiting behind B's token work, basically starved, while B sits comfortably inside the fair limit. So fairness here cannot be counted in requests. It has to be counted in token work, the actual prompt and output tokens each customer burns. There is a real research on exactly this, metering each customers by their input and output tokens instead of their request count. So the limits that actually hold up are written in tokens per minute, and the scheduler keeps a token budget per customer. So one heavy user cannot quietly eat the whole fleet. One request isn't one vote. It can be a sentence or a small book. So the gate can protect against overload and against unfairness, but there is a harder kind of protection, surviving when a GPU just dies. And they do die. They crash, run out of memory, hit hardware errors, a whole node drops off the network. So one worker fails right in the middle of streaming answers to real users. What happens? The first job is noticing fast. Health checks, constant little are you alive pings, so the router can pull that dead worker out of rotation before another request gets sent into black hole. But here is the real danger, and it's the one thing to remember from this whole section. Those requests just died. The clients retry them all at once, and each retry is a fresh, expensive prompt reading job, landing on workers that are already busy, which slows those workers down, which makes more requests timeout, which triggers even more retries. That's a retry storm. One dead GPU and the retries alone can knock over all the healthy workers behind it. And this is exactly where that admission gate ends its keep. It clamps down and protects the survivors from the stampede. And for the requests that were mid answer on the dead worker, there is no free lunch. You either restart them elsewhere and redo the expensive prefill, or if the system supports it, migrate them to a healthy worker and continue. One honest caveat, because people get hopeful here. There are warm failover tricks that keep the model weights loaded so a crashed process recovers without a full reload. That's a real and it helps, but it only covers the process dying while the card is still alive. A truly dead GPU or a lost node, it does nothing for. And even when it works, it does not preserve the live KV cache. So the half finished answers are gone anyway. So reliability here isn't the GPU never dies, it's noticing fast enough that the rest of the fleet doesn't die with it. So the fleet can route smartly and it can protect itself, say no, share fairly, survive a death. But every bit of that works with a fixed set of GPUs. So the slow loop is the one that changes that number. Sometimes the honest answer to everyone's overloaded isn't to reject more, it's to add machines, auto scaling, and again. We think we already know this one. Watch CPU usage, high means add a server, low means remove one, standard. But that rule quietly breaks here on two separate things. First, what do you even measure? On a normal web server, CPU is a great stand in for how busy am I. On a GPU running an LLM, CPU is a bad proxy. The GPU can look busy while doing barely useful work, or look calm while its queue is on fire. The signals that actually track user pain are the two clocks from the last video: time to first token and time between tokens, plus how full the KV cache is, and how deep the queue is. So an LLM autoscaler isn't watching CPU, it's watching those. It's a planner watching the things a user actually feels. And second, and this is the harder one, timing. On a web server, you are overloaded. You start a new instance. A few seconds later, it's taking traffic. No drama. But a GPU worker has to load the model weights first. Tens of GBs of storage onto the card and warm everything up. That can take, let's say, 40 seconds to a couple of minutes. So think about what that means if you wait until you are already overloaded to start a new GPU. You have lost. By the time it's ready, the spike has been burning first token times for a full minute. So the planner cannot just react, it has to predict. It watches the rate work is arriving, how fast demand is climbing, and starts bringing up capacity before the fire. So the GPU is warm by the time traffic needs it, and it will often keep a little warm capacity idle on purpose as a buffer, which feels wasteful. You are paying for GPUs that aren't fully busy, but that's a trade. A bit of idle GPU versus a wave of users watching a frozen spinner. So here is one more move the planner has, and it's a big one. Remember, prefill and decode want completely different things from the hardware. Long prompts pile up on the reading side, long answers and lots of streams pile up on the writing side. So VR slow isn't one problem. It is slow to start reading, or is it slow to keep writing? Different problem, different fix. And a good planner can grow those two sides separately. And some systems take that all the way. They put prefill on one set of GPUs and decode on another. Dedicated readers, dedicated writers, clean idea. Each pool gets hardware suited to its job, and one heavy prefill cannot stall everyone else's stream. But the moment you split them, you create a brand new problem, and it's a very distributed systems one. The KV cache. The memory the prefill worker itself just built now has to physically get to decode worker that's going to use it. In the last video, KV was just memory sitting on one card. Now it's a payload that has to travel across the network. So KV stopped doing memory and became traffic. And suddenly, where those two workers sit matters a lot. Same mission, the handoff is quick. Different missions across the network, the transfer costs real time. Sometimes enough to eat up the very first token savings you were chasing by splitting in the first place. So, placement becomes part of routing. Topology, aware transfer, fast interconnects, all in service of one line. Splitting the work is only worth if it is moving the memory is cheap enough. So disaggregation doesn't remove the bottleneck. It trades a memory problem for a networking one. So the slow loop is adding capacity, but capacity costs money, and the GPUs are stupidly expensive. So which one it buys matters. And the intuition here is backwards. The cheapest GPU is not the cheapest answer. A slower, cheaper card costs less per hour, sure. But if it misses your latency target, if users just sit there waiting, it's worthless for that job, however cheap it looked. And flip it around, the fastest, most expensive GPU isn't automatically the smart buy either. Running a tiny chat model on top end card is like renting a moving truck to deliver one letter. So the real move is actually a mix. Fast, expensive GPUs for the tight interactive traffic, cheaper ones for the relaxed batch work nobody is staring at. Match the hardware to the job, not to a spec sheet. The Melange paper showed exactly this. A mix of GPU types can come out cheaper than all premium fleet at the same latency targets. Because in the end, a cheap GPU that misses the SLO is the most expensive option there is. So we just built an elaborate machine. a scoring router, an admission gate, token fare limits, a predicting planner, split pools, failover. So let me ask the obvious question. Do you actually need all of it? And honestly, most of the time, no. One model, a few GPUs, modest traffic, no strict latency promise, basically one set of users, then VLLM behind a plain boring load balancer is genuinely fine. All of this ensits keep at specific scale. Many GPUs, many customers, real latency targets, bursty traffic, and lots of shade prefixes worth reusing. So don't build the airport if you are flying one plane. And one more honest note, because the fair question is okay, but is this how OpenAI or Anthropic actually serve their models? And the truthful answer is we don't know their exact stacks. And I'm not going to pretend to. But here is the tell. The open systems, NVIDIA's Dynamo, llm-d, the VLLM stack, SG-Lang, the Kubernetes inference gateway, all built by different teams, independently landed on the same three ideas: cache-aware routing, token-aware admission, phase-aware scaling. And when everyone building at this scale grows the same exact organs, that's not a coincidence. That's the shape of the problem. And it's just the real evidence for everything we just drew. So let us pull the whole thing together. And it's exactly the three loops we started with. When a request hits an LLM service, the platform is not really finding a free GPU. It's running these three loops at once, each one protecting something different. The fast loop is the router, pricing every request and picking the least bad worker, cache reuse against load. The protection loop is the fleet defending itself, saying no under overload, sharing fairly in tokens, not requests, and surviving a dead GPU before a retry storm takes the rest down. And the slow loop is the planner, predicting demand and adding the right GPUs before the clocks blow, and not after. And every one of the loops is really juggling the same five things, trying to keep them fighting too badly. First token time, next token time, cache reuse, fairness and cost. Push anyone and another pushes back. So here is the reframe to walk away with. Classic load balancing asked one question: which server is free? Model serving asks a much harder one. Given the two clocks running down and the money burning, what is the least bad decision I can make for this request right now? It was never about finding an ideal GPU. It's about buying the cheapest future before first token and next token run out. And once you see a serving cluster that way, the AI is slow, stops being a shrug, and it turns into a question you know exactly how to ask.